So I am only 90% sure that you can hear me. I hope you can.
Tony, we can hear you very well.
Okay. So sorry for this slow start here and the technical problems. I will shorten my talk so that we still finish on time. This is the title, and this is who I am. And I will give a few slides about the general question here. What is data science? And then I will give you some examples of the work I am doing that tries to do what I consider to be data science. So first, a very quick indication of who I am, since I've been asked to give this talk and asking you to consider my views on things. It's probably good if you see who I am. So this shows I do not have a linear career path. I started off in maths and engineering, veered left with chemistry to do medicine, veered away from that with a PhD in genetics, genomics, technology, then taught myself some coding languages and some computer science and started working on health-related data. In the Karolinska Institute, I set up their first biobank and a large-scale genotyping facility, but then realized what I was doing was technology. It was taking systems that we knew how they worked and applying them. It was not doing innovative science. I wanted to do innovative science, so I turned another corner and went back to maths and engineering in the form of data science. So as you see, jack of all trades, master of none, but I have a pretty broad understanding of all the relevant issues. So my main title is really about what is data science and does it even matter if we agree a definition? Well, I think it really does matter. If we're going to make progress, be productive and be successful, we really need a common understanding of what a topic is and is not. Funders need to know what they're funding, researchers need to know what they're doing and what funds they're asking for, consortia need to know who to bring in for different parts of the work, industry needs to understand what data science is, employers need to hire the right people for the right jobs, and the public need to know what we are actually doing when we talk about data science. We need a definition for data science. I tried to look up some information to see if there was a definition for data science. This is a list of training courses in data science. You see, it's data science and machine learning, data science and Python, data science and R programming. So this is not data science. This is technologies that you need to have expertise in if you want to do data science, but this is not data science. So I looked up some other sources of information. One site I found, the first one I found, said a data analyst explores data and does business administration, whereas a data scientist does exploratory data analysis, but also does data product engineering and machine learning algorithms. So this is saying data science is exploratory data analysis with IT, computer science, but using machine learning. I personally do not think data science should be limited to machine learning approaches, but it's a better definition. So I looked up the history of data science, and here you see up until sort of 25 years before the turn of the century, people were suggesting that data science is really just another name for computer science or just another name for advanced statistics. That's not what it is. It's much more than that. It then became trendy, and as you see, journals were launched with the title Data Science. The American Statistical Association section changed its title from Statistical Learning and Data Mining to Statistical Learning and Data Science. So everyone was jumping on the bandwagon, but there was no definition still. In 2019, Sophia Martin said, it's about breaking down big data into usable information and creating the software and algorithms to help exploit those data. That's coming close to a good definition, but there's still no consensus. Back in 2009, Jim Gray, the Turing Award winner, he argued that data science is a fourth paradigm of science. So that's not a data science definition, but it says something more about data science, that it's additional to empirical science, theoretical science, computational science. He now suggests there is data-driven science, but we don't have the definition. So I would propose here and now that data science should be recognized as a new interdisciplinary subject, which combines creation of new methods, technologies, software and data engineering, and statistical approaches to enable particularly large and challenging data sets to be maximally exploited. So that's quite a mouthful. Let me try to put that into pictures. I'm going to give an analogy of a Formula One racing team. For your institute, that's your XYZ institute. Regular statistics, data analysis, that's this. That's the application with traditional approaches. Very nice car, but not very good in a Formula One racing setup. If we want to do data science, we need to do much more demanding applications. Those applications need engineering. You need the guys to build the car. To do that engineering, you need to have the very latest methods, tools, equipment, materials, know-how. That trio of activities are the three levels that I think need to be included to be doing data science. And of course, it's a virtuous circle. What you learn from the applications, you go back and develop new methods, new capabilities. You get a virtuous circle. So it's methods, engineering, and demanding applications. That's my concept of data science, illustrated here. A simple example of that, just to ram home the point, something my group's working on. In terms of methods, we're looking at using artificial intelligence to cluster and group and find similar images amongst large data sets. The engineering is how you optimize that and deploy it effectively in clinical settings. And then the application is we use this to do prognostics on similar patients and rare disease patients. So looking at different facial appearances of rare disease patients, things like this. So that just gives you a sense of how those three levels are needed to do modern data science, in my view. Okay, I have about 15 minutes left, so I'll just quickly emphasize that in Leicester, where I work, we've broken that down further into the interdisciplinary parts, the impact-led aspects, sustainable aspects, reputational internationalization, and that helps us design our institute's strategy here for data science. And you might want to think about picking up some of these ideas for your own institute. Now I'm going to give you some real-world examples of that, which I hope you will find interesting, and you might get some ideas from this for how you can improve some of your own activities, or you might be interested in collaboration or adoption of some of the tools. The systems I'm presenting today here are all open source. So my focus in the group is on discovery, data science approaches to discovery. What do I mean by discovery? I mean discovery in the context of data reuse. Data reuse involves accessing data, analyzing data, finding the data in the first place. I've set them on three corners of a triangle because between any two, it's actually a continuum. If you do discovery the wrong way, you end up giving access or analysis when you don't intend to. So we're concentrating on how you do just pure discovery, which in no way exposes or shares or allows analysis of data, but it allows people to find the data or the samples and request them for secondary use. So it's just the discovery is the focus. Findability of valuable assets that could be used for secondary purposes. So I'm going to take those three levels, the engineering, the methods, and the applications, and give you a sense of how that fits into what my group is doing. On engineering, we essentially have built a platform. It's called Cafe Variome, or in the rare disease context, we just renamed it RD Nexus. It's a platform that is agnostic over what types of entities can be discovered, but it gives you all the different features you would need for safe, responsible discovery that doesn't enter into analysis or sharing activities unintentionally. It's been used in many projects to discover participants, so patients, biosamples, data sets, websites, experts, and so on, in many projects, as you see. There's a little logo on the top right, which is our Cafe Very own logo. This is how it works, and this is 10 years development in one slide, but essentially, here is the tool. You can see it has query interfaces, it has admin interfaces, it allows results to be displayed, it has a suite of query portals. It's all based on Keycloak authentication, authorization, identification. So that's a federated AAI system behind the scenes. The input data can come in any form. We filter and transform that automatically in the system and load it into whichever query engine is most suitable. Elasticsearch, Neo4j, MariaDB, and so on. So that's all comes in the box just with a simple Docker installation, and you can use whichever functions are of use in your application. This is how you can use it. In the middle, you see a network built out of these tools, out of these implementations as a peer-to-peer network. Each implementation can be a member of multiple networks. On the left, you can see that it works across firewalls safely by polling a trusted server. And on the right, you can see how it can be used with virtual nodes, data-free nodes, if the data you want to query to discover is separated into different components. For example, you might have the genomic data in one place, the clinical data in another place, the sample data in another place, and you want to do combined queries across them. That's also possible. So that's 2 slides, actually, not 1, sorry, on 10 years of engineering. But that system is up and running and available to anyone that wants it. Methods. First is you need a way to express those queries. So I've been co-leading with Jordi Ramler an international program with GA4GH on defining a standard way to express and respond to discovery queries. That's called Beacon 2. That was formally accepted as a global standard about 6 weeks ago. So that's now available. Secondly, we put a lot of innovation in how you can extend discovery queries beyond simple matching to similarity-based queries. That's illustrated here. The 2 characters in the middle here are identical. They both have difficulty walking. They both have macular degeneration. The individual on the left is similar, but not identical. This person has macular degeneration. She does not have difficulty walking. The person on the right is also similar, but in a different way. They have shuffling gait, which is similar to difficulty walking. They do not have macular degeneration. So in a query, you would like to be able to find these outside individuals, not just the internal 2 individuals. To solve that problem, we use ontologies, which provide an automatic structure for terms. Here's a simple phenotype ontology. You have each of these terms has an information content, depending on where it is on that tree, how big the tree is, and how often the term is used in a particular data set. I won't go into all the maths behind that, but just to point out that each term has information content, and that information content can relate it to other terms. We use that approach in a graph database structure. So here on the left is the HPO graph, sorry, a graph representation of the HPO ontology that I showed in the previous slide. When we add all these pairwise similarities based on information content, we now have over 3 million relationships, which are all handled and queried in real time by the system. That allows you to say, I want to find patients that are similar to some degree to a set of phenotypes. More importantly, it doesn't only have to be phenotypes. You can extend this same concept, and we have, to pathogenicity predictions, to gene families, to transcription levels, to different types of representations of genetic data, to cross-ontology mappings and biochemical pathways. Many things you can do once you start having these graph-based approaches and the concept of degrees of match, not just absolute match. So that's the methods we've put behind this system for discovery. Applications, my last few slides. First is an application in the SOLVA-D project. In this project, we have gathered together from around Europe data sets on 20,000 rare disease patients. Genomic data, as you see here, whole exome data, whole genome data, RNA sequence data, phenotypes, pedigrees, genes, pathways, epigenetics, metabolomics, and so on. These various data sets on these 20,000 patients are in one site. It's on the cloud. We call it the sandbox, where it's all available for analysis. And on top of this, we've layered our discovery platform that I've just shown you. That connects to an underlying representation of all the files, which is called RD3. So you have various types of query interface for demographics, for disease and phenotypes, for genetic variants, for the different sources within the system. And once a query is done, the result is returned as a count of matching patients, which you can then hand over. You get a handoff to the RD3 system to go to those relevant files and data sets, or you can just get information of the source and go and request collaboration. So that system is up and running today, but it's a centralized system. It's a discovery layer, powerful discovery layer using similarity on top of a large data set. The second application in Europe is the European Joint Program on Rare Disease. This is a 5-year program, 2/3 of the way through now, to make better resources for rare disease. This is a federated approach, not a centralized approach. And as you see, many different technologies, databases, systems have all been federated together, but many of them employ the Café Variome technology called RD Nexus in this project, or parts of it, to create exactly these kind of networks. It queries registries, biobanks, cell lines, model organisms, and so on. Each installation can join different networks for different projects and purposes. They can make them private, they can make them open. It allows for cohort building, advanced case matchmaking, hypothesis generation, and so on. But critically, although it's a federated system, all the data stay at home and only discovery, not analysis or sharing, is facilitated. The way that works is all users have to log in to a central portal to initiate queries in that federated system. The first step is that central portal contacts each of the installations. Those installations then communicate back to the login system to verify, validate that it's a genuine individual who has permissions, who is recognized by the system, so they're properly authenticated. And then they respond to those queries if they want to. If they do not want to, based on the user or based on the nature of the query, they do not have to. So all data stays at home, and all responses, all queries are responded to only if that home site is happy with that user and happy with the query they're making. Last but not least, one slide on here, a new project that's been running for just over 6 months. This is a European project, but it's part of a global network to collate and gather and make available data and samples for neurodegeneration. It's being done between research and the pharma industry and also Gates Ventures. And these are just some screen grabs from the website at the moment. We're building the platform, and the Café Variome system will provide the discovery layer in this environment. So this EP&D project, it will combine technology, security, and governance for real collective progress on neurodegenerative disease. That's really important. We're all getting older. We do not understand neurodegenerative diseases very well, and we have very poor treatments for them. So this will accelerate the discovery of diagnostics and treatments for these diseases. And as you can see there, it's building on an existing AD workbench that's funded by Gates Ventures that already exists in the States, and we're going to build this European component to connect to that. It will ensure data quality, it will create new standards for data sharing, and expand collaboration. So this is a very ambitious global program, And as I say, there's many parts to it, but the discovery layer will be built on this Cafe Varium approach. So I hope, I'll stop there. I hope you've understood what I mean by data science. We do need a definition of it. It's much more than clever statistical analysis. It's that whole spectrum of methods and innovations, including engineering, computer science, and applications that address complex and difficult data sets that are not easy to approach with traditional approaches. I hope that's of some interest to you, and I'll take questions in the last few minutes if you have any.